Good afternoon, everyone. Hope you can hear me.
Good afternoon, sir.
Afternoon. So we'll start up with the continuation of our last class, which is the lesson number 3, which we started after the lesson number 2, that is on the numerical descriptive measures, central tendency, and dispersion. Um, I hope you could recall what we completed up until last week. We were at the very introduction with the lesson number 1, and then we move on to lesson number 2, which is mainly on the presentation of data. So it did not have much calculations in the first 2 lessons, but you could understand that when we are going through the exam questions, when we are going through the exam questions, but still there can be sometimes 5 to 10 marks kind of a weightage allocated to these first couple of lessons. So with that foundation, last week we start the lesson number 3, which you're looking at right now, on the central tendency and dispersion. uh, if you could recall that we earmarked that there are 2 parts of this lecture. The first part, we took a start actually last week. We were having this conversation on the central tendency and measures of central tendency. And the second part of this lecture, hopefully we are planning to cover it during the next week. That is where we will talk about the dispersion and measures of dispersion. So the past papers discussion, after the today's lesson, there will be some questions, and after the next week lesson also, there will be some questions to be discussed. Okay, so that's the broader plan, which we were, sorry, let me try to level this a little bit. Okay, so that's the broader plan that we were working on, and with that in mind, we took a start on the central tendency. We discussed extensively on these 3 indicators, that mode, median, and mean are going to be some representers, sort of like an identifiers of a particular data set. So they, why do we do this? I mean, why do we try to calculate these things, identify these things? Is in order to give some sort of an indication of the data set that you're going to represent. Now, always don't forget the fact that we are working on the real world data. For instance, you've been given a data set of maybe some marks of a cricketer, okay, a Sri Lankan cricketer, batsman. Let's say for the past 20 matches, he has performed on a certain way. And then there's this 21st match, which you're about to see, and then you need to understand, okay, what sort of a score that this gentleman will be predicted to be played. So these indicators like the mode, median, and mean still can play some sort of an interesting value over there. Maybe you may see a pattern when you pile up all these 20 matches scores into a one single line. You may be able to identify that, okay, sometimes he may be scoring around 20s and 30s, whereas once or twice he has gone for a duck, maybe 0 or 1, and then couple of times he has scored maybe a century or a half a century. Then okay, when you put up all this data set, okay, this guy may hit around 30 to 35 marks, kind of a estimate you can easily get by just visualizing the data. So I mean, once you come to that conclusion, to that central number, okay, that this guy will play around maybe 30 to 35, how do you derive it? It's by simply looking at the central tendency of that particular data set. You don't say that maybe there are a couple of ducks, maybe zeros or ones. You can't uh, with a greater probability can't say that he will score not more than 1 or 2 marks. Or despite the fact that out of these 20 matches, if he has scored maybe 1 or 2 centuries, you can't predict that he will score a century for sure in this game. But uh, indicators like mode and median and mean is going to help you to uh, give a fair estimate that he may play around this kind of an average mark, this kind of a middle number. Hmm. So with that example, I just want to quote the fact that we don't really calculate these numbers just for the theory sake, but for the day-to-day usages also. Okay, so we discussed extensively about the very first simplest indicator, that is a mode. That is a most frequently occurring value. There will be single mode, dual modes, multiple no modes kind of instances. And interestingly, this is good for a qualitative data set as well as this is good for uh, non-extreme uh, impacted data sets. Say, for example, if there are a couple of extreme values, still the mode will not get impacted by that. So there are pluses and minuses of the mode, but then again, no numerical computation is involved. But then again, one of the simplest central tendency measure. The second one, which we discussed, is the middle point, the median. I mean, either you can put all the numbers set in an ascending manner or a descending manner and determine which is going to be the number which will come to the middle point. It's going to be pretty easy if you see some sort of a number like 5 or 7 or 3, where you can easily identify the middle as a number. But then again, even if you have an even number, still you can say fine, the third position and the fourth position divided by 2 is going to be the theoretical middle point. So that number doesn't always have to be a number in the data set, but it could be a derived number also. So both these indicators will not have some impact on the extreme values. Mind you, students, when you go to the exam questions today, you will see plenty of such instances being tested again and again by the recent examiners. So be mindful of these basic characteristics of median and mode. Then this is where we stopped last week, the class, by just giving a brief introduction on the mean. Now, students, this is the most important measure of central tendency in, I mean, from my perspective, simply because of the fact that we take into account all the numbers, divide them by the number of observations, and then only we derive this value. For that cricketers example, if you take these extreme values, the zeros, ones, and the middle ones, and then when you divide everything by the number of instances, that is 20 matches, you will get a good mean. That mean simply is going to be the number that you will see in these all these TV screens when they walk into the pitch with the bat in the hand. So that he has played 20 matches, and then this is the average score, something like 37.16. So this is one of the most popularly used number in the statistical arena. It's very simple how to calculate it is by taking the sigma, or the addition, summation of all the individual numbers, and divide them by the number of instances. It's a simpler arithmetic average. Okay. So, so for the both population and mean, sorry, population and sample, there won't be any difference at all. But only significant difference is that this capital N versus this simple N in such instances. The simple N is typically used to demarcate a sample, while the capital N is always demarcated to give the indication of that we're looking at the population data set. Okay. So let's try to move on from that point onwards. I hope you are clear up until here. We discuss one example also on the calculation part. If at all you have any doubts to be discussed, still you can disturb me and raise your question, or else you can use the chat also. I will look into it time to time. Okay. So let's move on. There are a lot more content to cover. I'm planning to pile up to at least slide number 39 or 40 today with the questions, so that comfortably we can finish off the session by the next week. Okay. Right. So this is where we are. We need to identify what are the characteristics of the mean. First one, it's a representative of total observations in a data set. Now these are minor points which are very, very important. Total observations. Unlike, if you take the mode, for instance, does it take the total observations into consideration? It does, in order to calculate the frequency. But then again, it omits all the other extreme values and zeros and ones, but it'll only focus on the most frequently occurring number. Unlike such indicators, even for the median for that fact also, median just look into the middle point. It doesn't really care what is happening on the other ends. So unlike these indicators, the mean will take into average of the all observations. So also now x bar is a popular representation of the mean. You can use the mean in an arithmetic functions, something like y equals m x bar plus c, kind of an algebraic functions. You can easily insert the mean. Mm. That doesn't necessarily mean that you can't put any other indicators like mode and median. Theoretically, you can, but this is a very uh, commonly, frequently used algebraic formation of the arithmetic mean. Mm. So look at this. Look at this bigger example. If you know a couple of means of the different samples or populations, you can combine them and easily calculate the uh, combined or the total mean of a data set. See, there are k number of data sets. Data set number 1, 2, 3, and up until data set number k. Then all what you do is that you have the average here. So average is going to be something like, let's say x bar is equal to 9 and number of observations are 10. Then this means n into x bar is going to give you 90. So these are such multiplications. You multiply the number of items by the arithmetic average or mean, then x bar, where you will get the total weight of that particular sample of population. And then likewise, you add up all these instances and then you divide them by the sigma of the total number of observations. So you may have a number 10 as the first data set. The second will be something like, let's say, 21. The third maybe something like 30. You take the addition of all these numbers, 10 plus 21 plus 30, up until the kth population's number of elements, and then you divide it. You will get the combined mean in such instances. Right. Can you do the same to medians and mode? It's difficult, isn't it? If you do that for the mode, you have to put everything into once again into a straight line and count how many instances. Using the straight line, you have to calculate what is the middle point. So unlike such instances, mean has a very unique usages like combining data sets or samples of population in that case. It's an identical measure, a unique measure. There are no multiple means for a given data set. There is only one unique. Why? Say in such instances like a mode, you have dual modes or multiple modes. There are no such instances. So this is a uniquely defined measure, the mean. So finally, it's a reliable measure which does not deviate much from the sample to the another sample. For instance, if you take the weight of baskets of mangoes, which you will have maybe 50 or 60 odd numbers in one single basket, when you calculate the average, you will not see much of a difference from one basket to the other basket. So these are some interesting characteristics of the mean as the one of the central tendency indicators. Right. So now, although this slide seems to be containing a little bit more theory, let's simply try to go through one by one, because at the discussion of the exam questions, you will see why these indicators are very much important. Okay. So these are some of the advantages and disadvantages and where to use, what to use, kind of couple of slides are there in ahead. Let's go through one by one and try to understand. First point. Mean is a good measure since it considers all observation of a data set and compared to the mode and median. So you could understand that while we just discuss at the means characteristics. It considers all the data set. Second point, mean and median are identical measures compared to the mode. That of course we discussed where in the mode there can be multiple no or dual kind of an instances. So those are not unique. Those can be replicated or null. Third point, given qualitative data, see qualitative data like a set of mangoes or a piece of clothes or shoes, qualitative, you can't have a numerical measure. Mean is a meaningless measure, while mode and median are still usable in such instances. Mode, how many, what is the most frequently occurring numbers? of maybe shirts and t-shirts and trousers, then you can say, okay, there are 10 shirts, and 2 trousers, and 3 t-shirts. So you can say, okay, fine. Shirts are the most frequently occurring thing in this particular data set. If at all you can put them in an order, you can still calculate a median also, even for a qualitative data set. But mean is going to be meaningless in such instances. So qualitative and mean doesn't go together. Okay. Fourth point. When there are open classes in frequency distributions, mean cannot be computed while mode and median are used. So we discussed that sometimes there are these groups, classes. So that when there are open classes, so like from negative infinity to this point, from this point to the positive infinity, still you can calculate indicators like median and mode, but mean will not have a meaningful value in such instances. Why? Because of the fact that you don't know that there will be many more data points in here. So that mean, if you are to calculate mean, we discussed that you have to take all the elements in the data set. But when there are open classes intervals, that means that there are to the negative end or to the positive end, there are open ends. So that you don't know what sort of data set is there. In such instances, you can't really calculate a mean. You can calculate for the given data set, but it may be wrong because of the fact that there may be many other data. Okay. Next point. Mean is highly influenced by extremely skewed values, while mode and median are not. Now, this is a very important point. When there is a data set like something like, let's say, 2, 3, 3, 4, 5, and then 1020. Now, see, because of this odd number, sorry, not the odd number, because of this extreme number, if you calculate mean, what is going to happen? Shall we just quickly take our calculators and try to calculate 2 plus 3 plus 3 plus 4 plus 5 plus 1020. How many elements are here? There are 6 elements. If I calculate the mean, I'm going to get a value something like 172.83. Now, is this a good representative? I mean, look at all these smaller numbers. You have 2, you have 3, 3, 4, and 5. Only one extreme number. But your average, now this is the mean, average is going to be a totally strange number. So that's why we say, even if you take a negative number, like, it doesn't have to be a positive number, something like negative 300. If you start like this, still you could have the same problem. Okay. So the point is, when there are extreme values, or a larger number among a set of smaller numbers, then the mode and median will not get affected. But then again, mean is going to be highly influenced. This is a classic example. Still, you can calculate mode as number 3 here, and median is going to be 3.5. Is the middle point, right? Okay, so that is, don't forget that this is a very important point, questionable in many instances. The next point, mean can be used as an algebraic function, but mode and median cannot be used as such. We just discussed. Mode and median can be defined graphically, but mean cannot be derived as such. Why? Later on, you will identify things like standard normal distribution when we are going to discuss the next class. So you will identify that the height, from the height of this data set, easily you can identify that this is going to be the mode. And say something like, if this is the 50th percentage demarcation, this is the 50th percent demarcation, you can identify this as the median. So graphically you can identify, but mean cannot be derived. You still have to calculate it. Okay. So despite the fact that we spend a lot of time here, these are important advantages, usages, and whatnot. Some more theories: when mean is useful as a good measure, if data is in qualitative, and if there are in the absence of skewed data and extreme values, in such instances, mean will be a useful answer. Sorry, now this point, uh, this has to be, you know, in a quantitative terms. If there are qualitative data, we discussed that mode and median is the only things to be calculated. Right. So both these indicators, median and mode, can be used if they are in qualitative points. If there are extreme values, you don't have to worry in such instances. Uh, so that if there has to be a decision to be made, sometimes you have to go with the most frequently occurring number. Now look at this point under mode. When decision should be made in abundance or no access to uh, all data, such as when determining a shoe size. For a shoemaker, you know that there are standard shoe size like size 8, size 9, 10, likewise. So you can't get a shoemaker to produce a shoe size like 8.7 or something like that. And for that shoemaker, who may be living in, let's say, Gaul district, he doesn't have much data as to what are the shoe sizes of the people he's going to cater. So he doesn't have all the data set to make a decision, but he doesn't have the mean, definitely no median, no point at all. So even the simplest indicators like mode is going to play a very important role in determining what to be produced in cases of sales, marketing instances. Right. So these two slides, don't forget that it contains some of the most interesting characteristics, usages, and do's and don'ts on the mean, median, and mode. That's on the total part of the measures of central tendency, mean, median, and mode, their characteristics, their usages, and advantages and disadvantages. Now we are going into the serious math part, where we are going to start the word on the dispersion. Now the word dispersion is going to give you a basic idea of how scattered or how centered the data set is going to be from one another. Simple as that. So if I just try to do a graphical illustration, if your data set is having a scatterness like this in a scale versus if a data set is going to have a centralized nature. Okay, so this is a pure babish uh, expression, but I just want to give you the idea that by dispersion, we are going to identify whether this particular data set is a scattered one and this is more of a centralized one. Scattered versus centralized. Okay, the nature of scatterness, I mean, of course, there are the word scattered, in fact, has a different meaning also. So you can't merely say that whether centralized versus decentralized kind of a comparison for the scatteredness. But then again, the broad idea is that if at all you have numbers everywhere, like zeros and ones to the thousands and millions, versus if you have numbers like that cricketers example, like 20s, 25s, 30s, couple of zeros and couple of hundreds. Likewise, you can compare the data set and get a good idea as to uh, the next point or the average or the representer or to express or to elaborate on the data set. That's why we are going to learn the idea of dispersion. The meaning, dispersion can be defined as the scattering nature of the data set uh, of a given data set. It could be the sample, it could be the population, anything. Second one, the extent of the observations being apart from the average values of the data set is explained by the dispersion. Now here in onwards, mostly we will be using the X bar or the average or the mean as the identifier of the data set. Now, when we discuss on the central tendency, we came to the conclusion, okay, fine. Except for these couple of problematic instances, like the qualitative instances, like the extreme value impacted instances, except for those instances, mean is going to be the best representative. So when we are going to discuss about dispersion, we have to select one indicator to be the representative of our data set. So from the point of view of that representer only, we will be discussing the dispersion. So that's why I have mentioned here, so that how apart from a particular data point, from the average or from the mean, is going to be our discussion in the dispersion. Okay. Third bullet, some uses of dispersion are ability to understand how the data is scattered, establish reliability of the measures of average, comparison of scattering data among few distributions, couple of distributions like which we just drew. Hmm. So these are some of the usages and practical instances of the dispersion. Okay, fine. Now these are the 3 or 4 measures of dispersion which we are going to learn one by one from this point onwards. The easiest one is the range, and then the mean deviation. Then we will discuss there are some limitations of the mean deviation. So because of the such limitations, we will find solutions always in statistics. We are going to learn 2 more indicators and wind up the day. That is the variance and the standard deviation. Mind you, these are now this is going to be one of the most important measures of your statistical career, where for any given data set, we'll discuss about the average and then discuss about the variance and the standard deviations in order to get an understanding of how the data is scattered or centralized or likewise. Okay. All right. The first one, that is a range. This is the first measure of dispersion. It's very pretty simple, like the mode, the definition of the mode. So this is the difference between the smallest and the largest item. Something like you have 2, 3, 5, 10, 20, and 30. So the range is the difference between these 2 items. 28 is the range in this data set. What's the idea? What's the broad idea? What is the smallest number and what is the largest number? So that once you look into this data set, you can identify whether it's a larger range relatively to the numbers that you're looking at or a smaller range. If you, in contrast, if you look into a data set like let's say 17, 18, 18.5, 19, and 20. Now this has a range of 3. Look at the absolute numbers also. It has 70s, 80s, 90s, and 20 with a smaller range, so that easily you can predict the next number is going to be in between these numbers. That doesn't necessarily have to be the case, but you can generally get an idea. So this is one of the easiest measure of dispersion. Just by looking at the number and comparing that number to the absolute numbers in your data set, you can get a good idea of how data is being dispersed. Okay, let's discuss some of the advantages and disadvantages. Advantages, very easy to compute. A simple measure. There are no equations for you to remember, just the difference between the large and the small. Again, ability to get a brief idea about the dispersion quickly. Likewise, we did. You don't necessarily have, I mean, for this data set, if you calculate, say something like the mean, and then you go on discussion on the advanced dispersion measures that we are going to learn, that's going to take a little time. But then again, if you quickly calculate the range, you can define, okay, how scattered or how centralized data from a qualitative perspective. From a qualitative perspective. Okay. Disadvantages: not being a representative measure since it does not consider all the observations. Likewise, the cases of a median and mode is in that so. It doesn't look into the central data, whether it has decimals or absolute numbers, zeros, ones, nothing. Just look into the smallest and the largest. So not a very good way to be a representative of a data set, but then again, that's how it is being done. Second point, it only considers the 2 extreme values of the data set, obviously. That's the same idea of the one just we discussed. It doesn't take into account of all the observations. Okay, fine. Now this is on the range. We don't have to go through the calculations. Simply, if at all you have to calculate the range, you take the max minus mean. That's the idea. Okay, now we are on the equation side. The first, sorry, the second dispersion measure that we are going to learn, the name of it is the mean deviation. Mean deviation. What's the idea? Mean deviation. So there has to be a mean x bar and how deviated from this particular x bar. Okay. The definition: average value of absolute deviations from the mean to each observation in a data set is known as the mean deviation. Average value of absolute deviation. Now, this is an important point to note, not the absolute deviation from the mean to each observation. This is the calculation. The mean deviation will be the modulus value. Now, what is this two signs that I have put here? Hmm? I mean, for instance, just forget about this ungrouped and grouped, which I will discuss in a while. But we'll try to break through this equation part by part and learn. Hmm? What's this idea of modulus value? Now, students, in mathematics, if at all you have a number, uh, say something like a subtraction, hmm? uh, 10 minus 3. We all know the value is going to be 7. Hmm? So, what about something like 3 minus 8? The idea is negative 5. Now, these are normal numbers. When you take the modulus value, when you put these two straight lines like this, these vertical lines like this, we are talking about the number, not the sign. The number, not the sign. So in this instance, 10 minus 3 is going to be still 7. No problem. Because despite the fact that 7 is there, this is written as plus 7. In mathematics, we typically don't write this plus sign, but rather we just write the number. It's like we write a number something like 210, but we all know that we discuss it to the leg of the 10th. But typically we don't put this number. We just briefly write the number so that we know that we are all discussing on the 10th log. Unless otherwise you take the logarithmic values and talk about the to the logarithmic of number 2, number 3, likewise. So these are silent and hidden assumptions in math. So if at all you write plus number 7 or 7, both are the same. But then again, if you write minus 5 and 5, this has two meanings. We all know that this is a positive number and this is a negative number, right? Fine. Now, this is okay. 10 minus 3 is 7. But then again, if you do the modulus value for this particular calculation, this is not going to be negative 5 anymore. It's going to be positive 5. Why? Simply because of the fact that we omit the sign. We omit the negative sign. You will understand it why we do it in a while. But just for the understanding sake, remember, we take the modulus value just to take the absolute number, forgetting the fact that there are positives and negatives. One of the best examples to explain this practical instance of this taking the modulus is the mean deviation itself. Keep the two equations, ungrouped and grouped, and let me show you a example. Look at this particular part. Now this is the data set we are looking at: 2, 3, 3, 3.5, 4, 5, 6.5, 7, 8, and 8. If you take out your calculators and try to calculate the mean, I know you may not do it. I really, I can't check whether you're going to do it. But if at all, you just take the calculator and get this to 10 numbers, add them up, and divide them by 10, you will get the mean of 5. Okay. So now look at the dispersion of this mean deviation that we have calculated. Forget about the sign. Look at the distance. Look at the distances. Now from 6.5 to 5, you have a distance of 1.5. Now try to understand in the simplest way. 1.5. How does this come? Between the distance from here to here. So from 5 to 7, it's going to be 2. This is it. Yeah. 5 to 8, it's a 3. Okay. And now look into this side. From 5 to 4, theoretically it's a negative 1. Theoretically negative 1.5, negative 2, negative 3. Okay. So now you will understand, okay, fine. We know the mean, and we can calculate the distance from mean to the individual values. That's all we know for the moment. Okay. What you mean by the calculation of the mean deviation is that we take all these deviations. We take this deviation, add them up, and divide by the number of occurrences. Look at an example. 8 minus 5. That's our equation. That's how our equation says. Xi minus x bar. See? Xi minus x bar. Xi is our individual value and x bar is our number. That's the average. Average is 5 in all these instances. 5, 5, 5, and 5. Then you simply take the subtraction or the deduction of the individual value and the average or the mean. Once you take those values, uh, I really want you guys to calculate now. Now calculate the without modulus value. Without the modulus value, if you calculate the uh, additions of all these individual numbers, this is the number that you're going to look into. 3 plus 3 plus 2 plus 1.5. These are the numbers that I just took into the equation. Plus negative 1 plus negative 1.5 plus negative 2 plus negative 2 plus negative 3. Can anyone tell me what's the answer here? Anyone? It's a simple answer. The answer is going to be 0. The answer is going to be 0. Why? Because of the fact that the dispersion is being taken into consideration without the modulus, without the number only. We have taken into account of the values of signs also into this particular calculation. I hope you are clear. If at all you take the summation, you're going to get the value of 0. But does this going to tell you any indication? You have the mean of 5. Okay, fine, you're happy. And the dispersion is 0. Can that be? If that is the case, all your values is going to be 5, 5, 5, 5. Likewise, the data set is going to be something like this. But that's not the case. You see, deviations from this side to this side. A lot of deviations are there. But then again, your data set is not going to be clearly explained if at all you're going to say that mean is 5 and dispersion is 0. Now, this is not a good thing to do. So that's why students, we simply take the modulus value. If you do that, all these signs are going to be converted into pluses. Why? We take only the value. We forget about the negatives. And in such instance, if you add them up, you will get the value of 19, the summation of 19. And then when you divide 19 by 10, you will get the mean deviation as 1.9. Now look at the value of 1.9. You say you have a data set with a mean of 5 and a mean deviation of 1.9. Something like negative 1.9 to this side, and again positive 1.9 to this side. Isn't this some sort of a good representer? So if you take a range approximately, now this is the area that I'm going to highlight. Now, by looking at the mean deviation and the mean, one can say, fine, okay, my data seems to be hovering around 5 to 3 to 7 kind of a range. Okay, that's the broader idea of this mean deviation. We simply take the modulus value of the individual value versus the average, the deduction or the subtraction, divide by the number of items, then you get the mean deviation. The only difference for this the grouped and ungrouped data set is that you don't see much of this being questioned, but then again, just for understanding, I'm always discussing for the group data and ungrouped data. If at all you're looking at a plain vanilla data set like what we just discussed, it is an ungrouped data set. There's no grouping. Grouping is simply something like 5 to 10, 10 to 15 kind of a instance. If at all there are such instances, you have to, the only difference is that instead of n, f or the frequency will come here. 3, 10, 15 to 20, something like 13. So instead of this individual numbers, now you know that there are three numbers of this particular group. Okay. So you take the representer for the individual groups, and then you do the same exercise for the mean deviation, and then the individual values will have to be multiplied by the frequencies. But seldom we see this kind of group discussion in your curriculum. So that's why I will stick to my equations in the ungrouped nature. Don't forget the fact that only difference to any of these equations we are going to discuss from here in onwards is that for the individual values, for the n's, it will be replaced by the frequency, and for these individual values, it will have to get multiplied by the frequency of the particular group, if at all we are discussing a group distribution. Okay. With that in mind, let me sum up the discussion on the mean deviation. You have the individual number, that is average, you calculate it, and then once that average is been known, then easily you can calculate the mean deviation by simply looking into the modulus value or the plus value, the sign only, sorry, without the sign value for the individual numbers, divide them by the number of items. So is the mean deviation only going to be a good indicator? Not only. You have to always discuss mean deviation with the mean, then only you will understand the nature of the dispersion. Okay. Now, these are some of the advantages and disadvantages of the mean deviation. Look at the first one. It's a good representative measure since all observations are taken into consideration, like the average. It is re-establishing the mean since it calculates a deviation from the mean to each data point. Like in our previous example, you know the mean is 5, and then once you know the mean deviation is 1.9, then you know, okay, fine, your mean is a good number. If you have mean of 5 and mean deviation of something like 600, you know, fine, your mean is not a good this thing. Why? Your dispersion seems to be significantly large from the number of 5, that is the simple average, which is in 1 digit, right? Likewise, you can either re-establish or you can argue whether the mean is a good measure or not for that particular data set by looking at the mean deviation. Disadvantage, the salient one that I can highlight is it is not a good algebraic measure since only absolute values of deviations are considered. Why? Because for a statistical data set, it is important to identify the negativity and positivity both to consideration at the same time. There's an answer on the C measure of dispersion, that is a variance and standard deviation, to answer this particular disadvantage. Okay, with that in mind, let's move on to the third and most important and most widely used indicator of statistical dispersion, that is variance and standard deviation. Now, for this discussion, you will understand that uh, uh, I mean, variance is the measure that we calculate by rho square, and standard deviation is nothing but the square root of this particular value. So despite the fact that we are discussing two things, this is almost the same and one and only the same thing, except the fact that variance and standard deviation is only being differed from one another by only a square root. You'll understand in a while why we have these two measures separately and why do we calculate them also. Okay, so we will learn the theory first. Variance is derived by calculating the average values of the squares of mean deviations. Now see the answer for that negativity problem. We take the squares. If at all you have a value like a can be a negative number or a positive number. What about the a to the power 2, a square? It is always a positive number. Why? If it is a, I mean, hold on. Yeah. If it is, let's say this is a negative number. If this is negative a multiplied by negative a, we know it's going to be positive a square. If it is a positive number, we know it is a multiplied by a, again a square. So that's why I argue, okay, when you take the square, it is always going to be a positive number. So we have the answer. Now we know that negativity cannot be addressed with the discussion of the mean deviation. So that's why we are identifying the next best measure, that is the variance. So this is derived by calculating the average values of the squares of the mean deviation. So simply, when you look into the equation, you will understand instead of that modulus number, now we will take the bracket and do a squaring. Next, relative of variance is the standard deviation. Standard deviation can be calculated by taking the positive square root of the variance. Positive square root, that's it. Simply the square root. Why? You will see in a little while. All right. Now these are interesting signs for you to keep in mind during the course. Now, for these two indicators, we are going to discuss for both sample and population. Sampling techniques, sampling methods, you can recall the difference between the sample and population. So this definition for variance and standard deviations is going to be marginally differ from one another. From symbol point of view, we are going to use S whenever we are using the sample variance, and then for the population, we are going to use this Greek sign of rho square as the variance and rho as the standard deviation. Okay, but still, I know for the fact that you still didn't get the answer as to why we are not going to use the simple one indicator of variance and standard deviation. Why two? The answer is, students, now once you look at the previous data set, it's here, yeah, this one. Now if you take the square values of all these numbers, these 3s and 2s and 1.5s, what is going to happen? You are defining from this particular plane of numbers to a whole different plane of numbers. Why? You're taking the square, you multiply one deviation 2 times. 3 into 3, 3 into 3, 2 into 2, 1.5 into 1.5. Likewise, once you get this number, so you are getting 19 here, you may get a number like 80 or 90 or 200, something like that. And then once you divide that by the number of observations, that absolute number that you are going to get is not in the plane of this particular data set that we are going to discuss. What is this plane? 2s, 3s, 4s, 5s, and 7s and 8. Now this is the plane. Once you multiply these numbers, you're looking into 4s, 9s, 16s, 25s, 49s, 64s, kind of a different, larger number set. So from this plane, when you take the squaring, and take the addition, you are moving this number set into a different plane. So your absolute definitions, the absolute descriptions or elaborations is going to be somewhat distorting, somewhat distorting. So that's why as the start, you take the variance, and for the explanatory purposes, you take the standard deviation. It's a simpler standard square root of the variance that we just calculate. So that's why you have two uh, different indicators, one for variance and standard deviation, despite the fact that both indicators are same. We start with the squaring and take in the variance. So simply the answer of variance, let's say for that example, you're getting a variance of something like 80. You take the square root of 80, and then your standard deviation is the measure that you can use for the explanatory purposes. So from statistics point of view, both these variance and standard deviations has their own uses. Their practical instances in the mathematical and statistical arena is going to be much wider than the discussion that we are going to have on this curriculum. The broad idea is that both are relatives, variance and standard deviations, same indicator. You take the deviation, take the square, divide by the number of instances. If you take the absolute number, that's the variance. That answer, if you take the square root, that's the standard deviation. Don't forget about the indicators of, the representators here. Right. So for this discussion purposes, let's forget about this group definition and focus on the ungrouped data. Not that you have to, completely forget from your memory, but simply remember the fact that typically the statistical definitions is for ungrouped data, raw data, absolute data. Okay, so what has happened here? Previously, you could see something like xi minus x bar. We took the modulus value divided by n. So instead of this modulus value, now you can see a bracket. This has converted into a bracket. And also, there's a squaring. What's the idea? Something like 8 minus 5. Previously, you take the modulus value of 3. Now, 8 minus 5, you take the square value, that is 9. It's a larger value now. You take all these larger values, 9 plus 16 plus 21 plus things like that, add them together, divide by the number of items. That's how you calculate the variance. The same equation, this exact same equation is what you see here. Isn't that so? You see a sigma, summation, I from 1 to I to the simple n. So this entire portion that I'm going to slowly highlight here is the variance. So what's the only difference? You've taken the square root. Okay, you've taken the square root. This is the equation. I mean, could you ask me the question that, sir, do we have to, remember this equation? I would say not remember. You have to use this every time from this point onwards up until the end of this curriculum. So that don't try to, memorize this formation. Just remember the fact that you have an individual value. You take the deviation from that value with the average, take the square. Simple as that. X minus x bar to the square. Okay, that's the definition on variance and standard deviation. Now this is an important theoretical part, which I don't intend to go to the roots or the explanatory, but you have to remember this fact. What's the broader the difference that you see here? You see that the wording of our previous discussion has come into play: population and sample. Look at the top part of these equations. These are same, right? These are same, same, same. What's the difference now? What is left? Capital N and simple n. Is that the difference? No. You see capital N versus simple n minus 1. That means for the population example, let's say for population n is something like 500. Hmm, okay, n can be applied here. So for simple n sample, this is the total population. Hmm. Then you take a smaller sample. Let's say n equals something like 25. Hmm. Can you take directly that n here? No, you have to take n minus 1. This is going to be not 25, 24 in this equation of variance and standard deviation. Students, now this is the only difference. Why? One could ask a sensible question: why for the population you don't? I mean, you take the individual numbers, individual elements, but for sample you take one item less. Why not n minus 2? Why not n minus 3 or 1.5? There is a deep statistical explanation for this. There is a, I mean, whole theory part. If at all you interesting, just do. I mean, if you just use YouTube and search about this n versus n minus 1 for population and sample variance and standard deviation, you will see good explanations by professors and academia, where this is not the explanation at this curriculum, this level. But then again, for curiosity, if at all you find time, I invite you to do a bit of browsing. The broader idea is that if you use the sample and if you use number 25 here, that value versus if you use 1 minus value, what's going to happen to the ultimate answer? Your sample variance and standard deviation is going to be marginally up. Why? Because of the fact that your denominator is going to have a slightly lesser value, 1 minus number. So statistically, there's a deeper explanation for this, and there's a rationale of this n versus n minus 1, which is going to give you a more correct value when you are using a sample. So it is not an option, it is a must to um, take 1 minus in instances like sample versus population. Okay. Interesting point to remember. Just don't get carried away. Simply, keep in mind the fact that x minus x bar, you take the square and divide by the number of items for any definitions. But be careful. If at all you're using the population, n is okay, fine. But if you're using the sample, n is going to be not that number. It is always going to be n minus 1. There are good, interesting MCQ questions in the exam questions. When we are discussing in a couple of while, you will see the application side of it. It's very tricky, but keep in mind. Okay, fine. Good example. There is one more additional point that I want to highlight here. Now, given a data set, what is this? Which one that you are going to use, n or n minus 1? In statistics, students, we always discuss this fact that we don't have access to the entire population. So population is going to be a special case, isn't that so? So something like a data set like this doesn't have to be always the population. Typically, we assume that all the given data set are sample, despite unless the fact that if it is mentioned categorically saying that you are looking at a population variance population data set. So in this question, that's why I just clearly mentioned that give me the sample variance and sample standard deviation. But in statistics, in your exam, in general correspondences, always remember the fact that you're looking at a sample, not the population. If at all the population is the data set that is mentioned here, then it has to be specifically mentioned. So unless otherwise, this is the equation that you are going to use always: sample standard deviation, sample variance. Okay, with that in mind, we'll take 2 minutes. I want you to do this math for me now. Calculate sample variance and sample standard deviation for the following data set. You have raw vanilla set of numbers. So it's up to you. Take a pen and a pencil and try to calculate this. How do we do it? I'll give you a bit of a head start. uh, for the I mean, forget about the standard deviation. We know that if you calculate the variance, then forget all the equations. We just take the number, take the square root using the calculator. That's a standard deviation, so that we don't have to take a rush for this part. We'll focus on the variance. What are the ingredients that we are going to use for the variance? We know xi minus x bar to the power and then divided by n minus 1. What's the only thing that we know at the moment? There are, I think, 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, 10 is known. So that means 10 minus 1. This is fine. Xi, fine, we know. These are the individual values. 37, 13. This is also known. What about the X bar? It's unknown for the moment. Can one of you tell me what is the X bar for this data set? Now, this is where you're going to be. You have to be faster. I'll show you there's another shortcut also in the calculator. Just remind me before the class, I will show you. I'm using a Casio FX991 series. There's a statistical mode where you can easily insert the data and get these values. For the double checking, it's always good to, at the exam, try to be familiar with this mode, stat mode of the calculator. Okay, taking too much time. What's the X bar? Do I see any answers in the chat? Is it that difficult? You simply have to add these numbers, divide by 10. 30 plus 7 plus 13 plus 21 plus 54 plus 33 plus 70 plus 14 plus 8 plus 10 divided by 10. I'm getting X bar of 26. Yeah, up to you. X bar as 26. Good. Great. Fine. Now you can do the math. You know the individual numbers. Xi, then you know the X bar. For instance, if you have 30, 26, I can calculate xi minus x bar, something like 4. Then in the next column, I can calculate xi minus x bar to the square. This is 16. Now this is one simple line. How many lines? There has to be 10 such lines. And once you complete this table, you should get a view like this. So for your reference, I'll just put this. Remember, at the exam, there's no alternative rather than to calculate. For MCQ, I really strongly suggest that you use the stat mode of your calculator. But for a marked question, I suggest that you follow this path. You have the individual LC, x minus x bar, then x minus mean to the 2. Sorry about this subscription. So likewise, you can add up all these deviations. So what's this number that you're looking at? This is the sigma. Sorry, what's this number? 4064. This is the sigma x minus x bars square. This is it. Okay, then the golden question. Is it divided by 10 or 9? I clearly ask, it's a sample. So that's why in your in this word calculation, you see the wording as 9, 4064 divided by 9. So this is the sample variance. Sample variance. Where did we start? We first start by calculating this mean. Then we came to the computation of the sigma, the total of these variations. Then we simply divide that by 10 minus 1 by 10 items. 10 minus 1 is the 9 that you see here. Okay. then you are going to get an answer something like 451.56. Forget about this 56 part. 451. Now, is this going to be a number which is in this particular data range? Hmm, not at all. Is that so? You have the range of single digits and two digits, sevens, eights, then tens, 14s. But look at this number, variance. What kind of an explanation that you can express from this variance? It's not really meaningful. But if you take your calculator and simply take the square root of this particular calculation, the square root of 451, then you're getting a standard deviation of 21.25. Forget about this 25 part, 21. Now what does this say? This has a, for this particular data set, has a x bar of 26 and a variation of 21. Pretty meaningful, right? You have 54s, 70s, see, and then also 7s, 10s, 8s. So that's why uh, standard deviation is going to be a better representer, since it is bringing back the deviation that we just squared and calculated into the plane of the uh, simplest data set itself. Okay. So that's how you simply do a raw calculation of sample variance and standard deviation. Before I forget, I really want to show you the calculator part also. In the calculator, you can shift the uh, if you press your mode button in your calculator, you should be seeing something like this. Hmm? Now in my calculator, I can uh, press number 3 and go into the statistical mode. So in statistical mode also, students, there are plenty of more statistical indicators like variance, covariance, linear regression, logarithmic, exponential numbers, likewise. I'm going to select the simple variance part. Now, once I am done with it, you're going to get a screen like this. Don't forget the fact that your calculator and my calculator can be something totally different. So once you have the data entry mode, you can simply plug in these numbers like 30. Then you press equal. It is going to get inserted to the data mode. Okay. So be familiar with your calculator. Now see, I'm simply entering the I'm simply entering the data of this question 37, 13, likewise. And once I entered all the data, let me just quickly show you itself. 54, 33, 70, 14, 8, and 10. Okay, I've inserted 10 data points, and then again your calculator will have option like this, where you can calculate some of the easier indicators like data, some variance, minimum, maximum distribution, like that. I'm going to go to variance and then ask for one of these indicators. So see, easily I'm going to get the answer of Sx, that is for the sample standard deviation of 21.24. So I strongly suggest that don't rely on this particular mode. So make sure, if at all you have the disposal of a calculator in your hand at the examination, you can easily, I'll come to you, Madi. So you can easily cross-check your calculation. The question which Imad is putting up is, how do you calculate the variance in the, I believe you're asking about the calculator. There is the mode for this data entry, and then once you are done with the data entry, again uh, in the bottom part of these letters you can find data like matrix, stat, complex, base. If you focus on the letter number one, yeah, shift and press number one, exactly, that's what I did. I pressed shift and number one, and then I entered into the mode of the statistical data. So you have the data, you have the minimum, maximum, the summation. If you get to go to something like summation, you will have the numbers like sigma x square, sigma x, which we will be heavily using in the next week. For instance, sigma x is from the calculator, you can easily get as 260. See, 260. So make sure, again, I invite, you may be having different modules of calculators. Just use YouTube and search for the statistical function of your calculator. Then there will be plenty of videos for you to follow up and be familiar. Again, I reiterate, why do we use the calculator? Two things. One is for the real world, you don't have to really go through a table and Excel and do the calculation. Even if you take the I could show you, but I'm going to shift my screen if that is the case. You can simply take the Excel, plug all these numbers and say equal SD. You can easily get the answer. In real world, students, in your workplaces, that is how you should do. But in instances like examination, there is no other alternative rather than to practice the manual method. And again, if you don't have a computer at your disposal, only if you have a pen and paper and a basic calculator, not even a scientific calculator, then what do you have to do? Again, there is no other alternative rather to use the equation. So that's why we are learning again, once again, to practice and apply at the examination. Okay. All right. Lot more theories to be discussed. So let's quickly rush on to the interesting parts. Right. The variance and standard deviation. Since all data are used in deriving variance and standard deviation, these are good representative measures. These are good representative. Extent of each observation deviated from the mean is taken into account, that we discuss. Taking square of real deviations, unlike absolute deviations, to avoid mean deviation being zero. See, this issue that we just discussed, mean deviation can be zero if at all you take the non-modulus value. This method is mathematically accurate. Deviations are overestimated in variance, but standard deviation takes out that weakness. See, over-evaluated. It takes into a different plane by squaring it. Once you take the square root of this, it is going to come back to the same plane, talaya. Standard deviation is the best measure of absolute deviations to compare different distributions. See, compare different distributions with same unit or similar means. You will see at the coefficient of variation. Now this is the part, we are going to stop the theories here. We are going to discuss this problem of what we just discussed at the last point. It's the best measure to absolute deviations to compare different distributions with same unit of similar means. But what if same units are not there or similar means are not there for two different data sets? It's not the same data set, not the same sample, two different data sets. Still you want to do a comparison. That's why, students, we have to now think of a alternative measure. This is not a I would say, although I have put it into the measures of dispersion, I would say this is simply reforming two dispersion methods we have just learned and identifying a relative measure so that you can do comparisons of two data sets with different means and different units and still come into conclusions. Right. Though using these measures of absolute dispersion to compare variations and distributions, data sets with different units, see, different units and significantly different means, not like 30s, 35s, you have a mean of 3 and 3000, significantly different from one another. In such instances, students, you still have a issue of identifying what sort of a dispersion from distribution A to distribution B. You can't merely use this absolute comparison like variance, like standard deviations, like average, and give a statistical idea. Or you can come into wrong conclusions in such instances. So that's why simply we manipulate two of our previously learned items. This is nothing but the standard deviation. This is nothing but the average or the mean. And then we express this as a percentage. So that's how you come into this coefficient of variation, which is the last dispersion measure that we are going to use. Now, what is this? This is going to be how, let's say something like 5%. What's this going to tell you? For 1 unit of mean or average, there is a 5% of deviation of the indicator that we are looking at. So if at all you have two data sets, something like data set A is going to have, let's say, data set A is going to have a uh, number like 5%, and data set B is going to have a number like 75%. Now you can say, fine, this is more centralized, this is more scattered. That conclusion now you can easily get. Data set A may be in kilometers, this may be in a different unit, but still you can compare these two and say, now these two are having either centralized or decentralized compared to one another. Okay, interesting. We can move on to questions, but I just really put up this exercise also. I really wanted you to try, but in the interest of time, and I understand that some of you may be lazy students to try these questions at class, I really want to show you the answer and discuss these two results, the interpretation part of the coefficient of variation. Then we will sum up what we discussed, and then we will move on to the exam questions. Okay, I just deliberately put these two numbers, two data sets, to show you that how either the average is going to be similar or the variance is going to be similar, but your absolute data set can be totally different from one another. So without looking at the nature of the data, if you come into a conclusion of the similarity or disparity of the data set, you can come into wrong conclusion. So that's why I just really want to put some simple numbers and show you the calculations of the average, standard deviation, and this last interesting number that we just discussed on the coefficient of variation, this relative measure, the percentage, and show you how we are going to get different interpretations. Okay, fine. We will discuss the data set right now, and then we'll quickly move on to the answer. Okay, but I strongly suggest, again and again, I suggest I don't go to the exam, whereas you will be, facing a difficult time at the exam if at all you find calculator is not familiar or numbers are not very familiar to you. So use your time, uh, look into my explanation, look into my slides, and then do your math on your own. I have just used Excel and calculate the perfect number for the explanatory purposes. Okay, the first data set X is having three numbers, 1, 2, and 3. Y is having another three numbers, 101, 102, 103. In the face value of it, you will see, okay, fine, these data sets seem to be pretty much gelled together, but numbers are at two different planes. Ones and twos, these are single digits, whereas 101s, 102s are three-digit numbers. That's all what we can comment at this instance. Look at number two, data set number two, country A, country B. You are having fuel prices. Now this may be United States, and this may be a country like Indonesia, where they are having 5-digit and 6-digit numbers typically. Look at the numbers, 270, 306, kind of a decimal numbers. Country A may be a strong currency country, and country B seems to be a weaker currency country, whereas their prices are 11,000. This may be, let's say, monthly prices or average annual prices, something like this. Now, with this data set in mind, we will go to the comparison purpose and identify what we can derive. So data set 1 and 2 of the first example, I have just quickly calculated the, I mean, I don't really want to show you the numerical part. I'll just purely use the Excel and put up an equal sign and put average of this data set 1, 2, 3, and average is going to be 2. 1 plus 2 plus 3, 6 divided by 3 is going to be 2. Sample standard deviation. Don't forget the fact that I'm going to assume that this is a sample. How do you calculate? So this is the mean. This is going to be 1 minus 2 square, 2 minus 2 square, 3 minus 1 square, square root divided by 2. 3 minus 1, right? Remember, 3 minus 1. What's the answer? This is 1 plus 0 plus 1 divided by 2 to the square. 2, 2 square. Answer is 1. That's how you get the correct. Thank you very much. That's how you get the sample standard deviation as 1. Similarly, look into the other calculations. Mean 101, 102, 103 divided by 3. This is the middle point. 102 is going to be the mean. If you do the same math to the sample standard deviation of set 2, aren't you getting the same numbers? Isn't that so? 101 minus 102 plus 102 minus 102. So this is eventually going to be 0. Well, let's forget about it. 103 minus 102. You square it divided by 2 and take the square root or to the power half. Both are same, huh? Half or square root. It's also going to be 2 divided by 2 to the square. That's also 1. Now see, you have a mean of 2 and a sample standard deviation of 1. Without the 1, why is the mean different? Exactly, correct. Good point. That's exactly what I'm going to highlight on this discussion. See, the mean is pretty much different from one another, but the standard deviation is going to be the same. What does this going to tell you? I mean, just look into this simple data set and try to understand. From 2, we have a sample standard deviation of 1. Okay, approximately 1 deviation. You can identify the data set. Here also, mean of 1 or 2 and with a deviation of 1. You can see the other data. That's a broader idea of standard deviation. From this point onwards, when we go to a standard normal curve, you will learn how many standard deviations that statistically this data set is going to get dispersed from. Rho minus 1 standard deviation to this side, rho minus another standard deviation to this side. So we learned that approximately 60% of the data set is like this, approximately 97% of the data is like this. Likewise, we are going to learn how many standard deviations that your data set is going to differ from one another. But for the, I mean, till we go there, simply try to understand, okay, from the point of view of absolute data, fine, your deviation is 1. By looking at the data set also we can find it, isn't that so? We are comparing 1 or 2 versus 1. 2 versus 1. But if you look into the relative dispersion, you will see if you divide sample mean, sorry, this has to be standard, sorry, this is wrong actually, standard deviation divided by mean. Sorry about this. So when you divide the sample standard deviation by mean, look at these answers that you are getting at. 50% here, 1% here. Now look at the interesting description. What does this going to tell you? Although your data set is in single digits or 3 digits, or they are in the similar nature, you can identify from 2 to 3. If you move your cursor from 2 to 3, there is a something like a 50% moving from one number to the other number. It's like your car is value of 2 million and it moved rapidly to 3 million. 50% variation. Your car is 2 million, market has gone down, your car is coming down to 1 million. 50% variation. That's why we need to calculate this coefficient of variation and do the comparison. See, look at the standard deviation is same. Data is deviating from one single unit. But if you look into the relative dispersion, you can see this data set is having a very high deviation from the mean to the next point. But in contrast, if you look at this calculation, how do you calculate this? 1 divided by 102. So approximately this is going to be 1%. Like 1 divided by 100, isn't that so? This has to be something like 0 point something, close to 1%. What does this going to tell you? This is going to tell you, okay, I have a mean of 102, standard deviation of 1, and my relative dispersion is also very small. This is not 102 to 204. This is not 102 to 1. It's 102 to 101, 102 to 103. Smaller distribution, smaller deviation, smaller variation. So that's why, students, we need to calculate the coefficient of variation and then elaborate on the variation of the data set. When you do the comparison, you will see, despite the fact that your 1, 2, 3 is having a standard deviation of 1 and this data set is having a standard deviation of 1, doesn't mean that their relative dispersion is the same. The absolute dispersion, the numbers, numerics are same, 1 and 1. But relatively, if you calculate it relatively, your deviation is going to be very much larger in one data set and very much smaller in one data set. So this is the pure learning I want to share with you from the data set 1. Data set 1, what we looked into is simple vanilla raw numbers in two different planes. I just want to show you, if you despite the fact that you get a similar standard deviation or almost alike, 1 versus 2, 1 versus 1.5, you can say these are similar much standard deviations, but your relative dispersion is going to be a total different ball game if you do the math and see. Okay, second data set, this fuel price example. Now this one, I want to show you the reciprocal, just the reciprocal, the opposite side. Look into this data set, 2.0s, 3s, and forget about the calculation, I've done it for you. You're getting a mean of 2.81 here and a mean of 12,385 here. These seems to be in the same plane, not a problem. Standard deviation, 0.16, 638. These two are in different planes right now. Isn't that so? Not the similar standard deviation. But now look into the coefficient of variation. How do you calculate it? Standard deviation divided by the mean. Standard deviation divided by the mean. Now you see. Your coefficient of variation is pretty much similar. 6%, 5%, pretty much alike. Now, students, you can comment, okay, fine. Unlike the data set we just look into of these two data sets, these two data sets, although their numbers are at an extreme ends, 2 point something, 3 point something to 12,000 and 11,000 numbers. But still, when you do the math and calculate the coefficient of variation, you may see, okay, these data sets seems to be having a similar nature of a variation. Similar nature of a variation. You see the absolute point of view, the previous data set, ones and twos and 101s and 102s seems to be having a similar variation just by one absolute one movement, 1 to 2, 2 to 3, 101 to 102, 102 to 103, just one digit. But these numbers, from the naked eye, you can't really identify 2.87 to 3.06. We can't really, measure to the eye level. But then again, when you calculate the coefficient of variation, you will see their relative dispersion seems to be pretty much similar. Sort of like when the global oil prices are moving from one point to the another point, both countries seems to be having a similar impact. So that's why from the vanilla point of view, if you just look into the numbers, you can't comment on anything. But when you calculate the coefficient of variation, then you can jolly well compare the data set and comment on whether you're looking at a data set of having a significant impact versus a minor impact versus a similar impact to one another. I do believe that this is a good learning. So the whole idea is that never come to conclusions, never jump to conclusions without calculating all your measures of dispersion, average, standard deviation and variation, and coefficient of variation. And when you calculate all these numbers only, you can comment about a data set, you can derive conclusions, you can make decisions. Okay, I'm on track, I'm on plan. I have half an hour to do a lot of questions with you. If I can take a pause and see whether if you have any doubts to be clarified. Okay, great. And if you don't have any Doubts, we have plenty of questions to try for the next 2 hours. Sorry, just kidding. Half an hour. Okay, great. So, question time. Um, Thank you for patiently, you know, listening to the theories. Some of them seems to be a bit boring, but when you find from question to the question, you will understand what I meant and what sort of importances are there in these hidden points of these qualities, advantages, disadvantages, users, do's and don'ts, and whatnot. 19th September. Now, I hope you must be familiar with the question structure of the exam paper. Uh, Whenever there is a subpart, that means I'm looking at the question number 1. That's your compulsory question, MCQ part. Okay. Question number 3. The quality control manager of how many marks? 2 marks. Huh? Quality control manager of a LED bulb company samples 100 LED bulbs and find the following set of data. Now, what are these? 8-watt bulbs, 13-watt bulbs, 17-watt bulbs, 20. Now, these are different batches, isn't that so? Look at the means, the lifetime. Um, mm, yeah, he's looking at the, I believe, must be looking at the number of hours, isn't that so? 8, yeah, number of hours. Number of hours is huge. So this may be, let's say, 450 hours or kilowatt hours or something like that. Look at the means. These means are not in a similar range, so you can't merely compare. And the standard deviations are in, okay, great. I see some people are trying, thank you. Standard deviations are also in different numbers. You can't make a conclusion. The question is asking which type of bulb has the highest value for coefficient of variation. It's a direct ask, I would say, highest value. But there are this portion of highest value, lowest variation, highest variation, maximum, minimum. This coefficient of variation question can be put into different way. Just try to understand whether you have to look into the maximum number or the minimum number. Simply, what do we have to do here? In the interest of time, I'm going to share you my working. You have to calculate the standard deviation divided by mean. This is the coefficient of variation. Once you do the math, you will get 0.01, 0.015, 0.009, 0094. 3 digits gone, 3 digits gone, 2 digits, and this is the maximum value. And now this seems to be the bulb which is having the maximum variation, highest value for coefficient of variation, or the maximum variation between the mean and the numbers that you are going to observe. Look at the numbers, even 1600 versus 15. Now 15 seems to be a bigger number compared to 12, right? But when you do the ratio, this ratio to this ratio, this is the bigger, not the absolutely larger number. So the maximum deviation you will see from the point of view of these 4 data set is answer B, 13-watt bulbs. Okay. Question number 2, 19th September, part number 4. This 19th September paper, there are plenty of MCQ questions on your theoretical questions of this part number, lesson number 3 on dispersion. Arithmetic mean is representative of the whole data set. Is that a correct statement? We know that's a correct statement. The median value must always be a number in the original data set. Can it be the case? Must always be a number in the original data set. It can be a plus b divided by 2. 30 plus 32 divided by 2, kind of an instance, where when you have an even number of data points. So I have to disagree with that statement. Or C, an arithmetic mean is affected by extremely values. That part is correct, isn't that so? When there are extreme values, arithmetic mean is going to get distorted. While median is unaffected by extreme values. That is also correct. Median is not affected by the extreme values. The mode is the only measure of central tendency that can be used if the data set is not in numbers. This also I have to agree. So I have a worked example here. Yeah, this is the case. And see the last point. Example, something like number of fruits, 10 mangoes and 11 apples. You can still take the mode, but the other indicators are not going to make sense. Even the median, you can't put all the apples and oranges in a line. You don't know which one to put first in that. So in that instance, mode is the only useful measure. So my suggested answer is answer number C. A, C, and D are true. 19 September, question number 4. Again 5. A joining question. A joining question for another 2 marks. Consider the following statement, and the examiner is asking which of the following is correct. Which of the following is correct? Hmm? Mode is defined as the most frequently occurring value in the distribution. We can agree. Mean does not require measurement of all observations. Mean does not require measurement of all observations. We cannot agree for this. Mean does require measurement on all observations. Okay. C. Mean is uniquely and comprehensively defined. Now you could recall that we have discussed exact similar statements in the theory, right? We can agree. Both mean and median are not affected by extreme values. Median I can agree, but mean is going to get affected by the extreme values. Correct? Getting an answer of A, which I can suggest A and C are correct. Mean is wrong, median is correct in this last statement. See, for a good 2 marks, you can easily remember the theories of mean, median, and mode, and then apply the same. Now, this is a good question. A similar question is recently being tested in the 21 January paper also. Try to understand this question. Now, one could argue with me here, but then again, there's only one correct statistical answer for a numerical question, so that we will try to derive why and how we can conclude. Following observations were made on average daytime. Okay, good. Keep on trying. Following observations were made on average daytime temperature X in Celsius. The data in Kandy in June 2019. Look at these points carefully. Kandy in June 2019. Daytime temperature. Okay. What are these? Xi sigma. This seems to be the addition of all the individual, maybe 30. Yeah, 30 is the observation. And the summation is 616. Xi minus x bar to the square is 58. What is this? This is the top portion of the variance calculations, isn't that so? Top portion of the variance calculation. How do we, what are the asking points? The average and the variance. Average is going to be nothing but the something like sigma xi divided by n, and the standard deviation is going to be, now this is the point I want you to focus on, sigma divided by n minus 1. This is the golden question. n minus 1. Looking at the answer, students, you may see there are two Celsiuses and two 1.9 Celsius. So one can easily guess, okay, for n is equal to n, there is going to be one answer. It's going to be 2 Celsius, and n minus 1, there's going to be another set of answers. I told you explicitly, if at all not mentioned, you're looking at the population, you have to always assume that you're looking at the sample. And also from common sense also, you can argue, okay, fine, June 2019 seems to be only 1 month, and there can be many more data points to be observed. Likewise, also, you can come to a conclusion, okay, fine, this is a sample data set. Unless explicitly mentioned, it is the population. Always in the statistics, you have to take it as the sample. Okay, I see some people are trying. I appreciate it. Thank you. So this is my marked answer. I'm going to tell you that not given as the population, so I have to assume that this is sample, and that's why I have to take n minus 1. Average is going to be 660 divided by, is it 29 now? No, for average No impact. Only the standard deviation and variance equation only we have this argument n versus n minus 1. Hmm? So average divided by 30, 22. So either this or this is going to be the answer. The standard deviation 58 divided by 29 and not 30. So that's why A is going to be the answer and not B. Okay, it's a good question. Think a couple of times and try to digest the idea of why we are not looking at the population equation. Hmm? Correct. I understand Iman this problem. That's a broad idea. I think that's the same reason that this is the 2019 September paper, and a similar question is being tested at the recent paper also. We'll try to look into that question also if the time permits. Correct. So that's the broad idea. Don't forget the fact that for a equation, when there are two forms, two natures, always try to keep in mind the rationale. So logically, if at all you've been telling that this is the population, then you can use the population equations. Unless otherwise, always assume that we are working with a sample. So that's why the answer is going to be A and not B. All right, interesting question. Uh, Only been seen in twice in the recent papers. So be careful. Why I meant is being careful is that similar nature can be questioned in a different form. Examiners can be creative. It's a mathematics paper. End of the day. Yeah. 19 March, the adjoining paper. In the following data series, the median was calculated as 40. It's a very tricky question. There are multiple ways to get this answer correct, but I will show you one of the most rational and simplest and easiest way to argue here. Median calculated as 40, and this problematic x value is there, and unfortunately, examiner is asking the same thing. What is the answer for the x? If I try to rationalize it, 30, 32, 3, 4. This is a even number case. So my median is going to be, sorry, don't get me wrong, it's not 12 and 76. We have to put them in an ascending order. My median is going to be a calculated number. That's why it's been said it's calculated as 40. Okay. So what I had to do is logically, I had to put these numbers in a line and argue. So I done the first part here. See, I put, we can put each value, hold on. We can put each value for x and correct. So eventually, yes, that's that's the same thing that I'm trying to do also here, but I'm going to explain it in a bit more logical and a rational way. Okay, I put everything in an ascending order and I'm going to argue, okay, where my median is going to be. See, 6, 12, 24, 34, this segment is fine, and 98, 78, 56, 44, and this segment is also fine. Now this x, I don't know where 40 is going to be lie on, because 40 is a calculated number, and also x could be anywhere. X could be anywhere, but I can tell you one thing for sure. This number 40 is not in the data set, isn't that so? So that means x cannot be located in an area like here. Why? What's the case? Because in such instances, either you have to take 34 plus 39 and divide by 2 and get all these two values divided by 2 and get the value of 40. But none of them are going to give you the average of 40, isn't that so? 39 plus 44, a different number, 42 point something. 34 plus this thing, 30 something. It's not 40. So I can jolly well argue, fine, this is going to be either of these instances. Either 39 plus x divided by 2 is going to give me a 40, or 44 plus x is divided by 2 to get me the value of 40. Both these instances can be true, isn't that so? So if 44 plus some number is going to divided by 2 is going to give me 40, this has to be what? This has to be 36. Isn't that so? 36 to 40, 40 to 44. Midpoint. So do I see an answer like 36? So obviously, no, 36, 36, 36, no. So this is not going to be the case. So I can jolly well say, no, this path 44 and x is not going to be getting paired. So easily I can argue, okay, 39 and x is going to be the pair that I'm going to look into. All what I know, I have to get a median of 40, and this x is going to be somewhere near 39. And we can comfortably argue, okay, fine. If x is 41, I'm just looking at the answer. If x is 41, then we can comfortably find the middle point of 39 and 41 and x as the 41, and my x is 41, and in such instances my median is going to be 40. So I would recall that this question, I mean, you can apply different equations and also come into this position of the sixth position or seventh position, but comfortably you can argue, or you can do a trial and error like Iman is suggesting. You can do a trial and error and see. I mean, this branch, obviously you don't have to go through this whole part. Why? Because that if at all you have to get the 44 plus x divided by 2 as 40, then x has to be 36. Then 36 is not given an answer. Yeah. So definitely it has to be 39 oriented answer. Now we know that 39 and 41 is the only method that you can bring up a 40 to the picture. 39 and 41. Otherwise 39 and 38, 39 and 37, no. It's a value less than 40. So that's how I can jolly well get the answer. X as 41 to get the median as 40. Sort of like a general knowledge question, but then again, we have to argue from the point of view of statistics, the median, the middle point, the calculated one. If it is in the data set, it's a different argument. If it is a derived number in an even distribution, it's a different argument. That's the whole learning here. I hope it's a interesting learning. Okay. All right. Lot more theory questions. I'm going to skip some of them and to come into interesting parts and quickly show you the answer. The mode. This is the only measure of central tendency that can be used in the data, not in numbers. Now, these statements again and again we have discussed. Agree. Defined as the most frequently occurring number. Agree. Some distributions have several modes. ASI. Multiple modes, dual modes, no mode. Agree. It's a middle point. No, mode is not the middle point. So A, B, and C are true. Okay. Quickly skip into the interesting questions. Coefficient of variation. Now, this question, students, I'm being a bit unfair to you at the moment because of the other couple of parts will be discussed only after the next session. But for the moment, let me share you the argument. What is the coefficient of variation? It's the standard deviation to the average relative measure for single variable. For single variable x, x1, x2, x3 likewise. The other things that we are explained here under the answer B and C and T, all these are for two variables, x and y, P and Q, A and B, two variables, height and weight. So the only logical answer you may know at the point is the answer number A, which is a relative dispersion, the percentage, Pratishata. That's the only thing that you can tell at the moment. So I'm sorry for being not fair, putting up this question without discussing the other part. But we will be learning these things in a little while in the next class. The strength of a relationship between two variables, we are going to learn it as the correlation coefficient. The simple R to the xy. This is relative measure of x's and y, the relationship between two variables. Not the correlation between two variables, no, single variable. The percentage variation in one variable caused by the variation of another variable, no, again two variable discussion. So we can only agree for part A. Okay. So we could say still, you know the coefficient of variation, and you know that, okay, fine, only the A is the one that it can do. So with that point also, you can come to a conclusion. More theoretical questions. We'll quickly look into the answer. Arithmetic mean, representative whole data set can agree. Median value must always be a number. No, not could be the case of a derived number of A plus B divided by 2. Arithmetic mean is affected by extreme values. Agree. While median is unaffected, agree. Mode is the only average that can be used if the data set is not in numbers. That also can be agreed. So A, C, and D are true is the correct answer. Moving on quickly. Which of the following is an example of a relative measure of dispersion? Now these are the ones that you are going to learn on the next week. Sorry. Now all these things we have learned. Standard deviation, variance, coefficient of variation. Now this question is asking for a relative measure. Standard deviation is an absolute measure. Absolute numbers, 3, 4, 5 kind of. Variance is also absolute numbers, 3, 10 likewise. Coefficient of variation is a percentage, relative measure, 5%, 30% versus 2%. Now this is a relative measure. So coefficient of variation is the answer. Coefficient of variation. Now this question, I really wanted you guys to try, but being lazy students, I know that you may not try, but with my explanation, just try to there are a couple of more questions in the latter part. I will leave those questions to you. I'll try to do this question and we will discuss the logic. Arithmetic mean of 8 numbers is 3. What does this going to tell you? Sigma, I will take a total, something like sigma xi divided by 8 is 3. Isn't that so? So this is, I will take x up until 8. So sorry about this lazy notation. Okay, sorry about this whole part. Let me just put it into nicer way. Sigma of total of 8 numbers divided by 8 is going to be 3. A ninth number is added so that the mean is changed to 4. Sigma t 8 plus a ninth number x. Then I have to divide this by 9, isn't that so? Why now there are 9 numbers? Now this is the mathematical representation. A 10th number y is added. It's giving me more problems. 8x plus y divided by 10 is going to give me another mean. Be watchful. 8 numbers were there, 9 numbers were there, and now 10 numbers are there. It was the addition of first x and then it was the addition of y. Is asking what's the value for x and y. Pretty simple. We can get this part sorted first, isn't that so? What's the total of these 8 numbers? Sigma t8 is going to be 24. Correct. If this is 24, what's the value for x? This is 24. X is going to be this side 36. 36 minus 24, correct? Very correct. 36 minus 24, x is going to be 12. Correct. Now we know that this part is 24. We know that this part is 12, 36 here. 36 plus y is equal to 45. 45. Y is equal to 45 minus 36. Y is going to be 9. That's the answer. Do I have the, yeah, my suggested answer, x is equal to 12 and y is equal to 9. Interesting question, isn't that so? See how creative an examiner can be. Sort of like common sense questions. You can play around with the numbers of mean and add into more difficult questions. 19 March. This question we will try to skip it to show the answer. Answer number A, C, and D are correct. We have discussed this again and again. Now this question I want you to try at home. Arithmetic mean of 9 numbers is 3. 10th number x is added so that the mean changed to 4. 11th number is added. Now the mean changed back to 3. It's interesting, this thing. Calculate the value for x and y. Try it on your own. In the interest of time, we will try to discuss few more interesting questions. Operations manager of a cargo company samples 100 packages and find the following data. 100 different packages. And now look at the indicators that he is going to calculate. Height in meters, width in meters, weight in kilograms, and volume in cubic meters. Different indicators. And eventually, let's calculate the mean and the standard deviation. And the asking part is which parameter has the highest variation? See, highest variation. What do you have to do? You have to calculate the coefficient of variation and take the maximum value. Highest variation, maximum coefficient of variation. Relatively, percentage wise. So you take the coefficient of variation by taking the standard deviation divided by mean, and you have to take it to the percentage. I'm a lazy bum. I just calculated with the decimals and I'm putting up the argument. So this is 10%, 20%, 24%, and 12.5%. So 24.4% weight is having the maximum variation. The answer is C. Answer is C. Okay. So mostly you can see when the units are not in the similar way and the means are pretty much different. See, means of twos and ones and fours. Now you may compare these three, but what about the weight? Total different number in a different plane, different number of digits. So always you have to, in such instances, if you are comparing or commenting or making a decision on anything, you have to always go for the coefficient of variation. That's the only relative measure of dispersion we know. Good question. We'll try this. Following data represent the number of internet failures observed in a day in a bank branch for past 2 weeks. Two failures, six failures, zero, and there's this extreme of 16 number also I can see. So this seems to be a fairly broken day. 16 times the internet has gone. Consider the following statements. The mode is 2. The most common occurrence is having 2 internet failures in a day. The median number of internet failure is 3. For this data, median mode better measures central tendency than the mean. For any of this, I think we have to first do it in a order because he's asking about a median also. So the mode I can calculate. Okay, there are there are 5 times of 2 being repeating. So mode is 2. We can agree. Most commonly occurred number is also 2 internet failures. That statement is also correct. And median point is also, it's going to be a calculated number, but then again it's going to be also 3, while 3 twos are there. And this is the interesting point. For these data, median and mode better measure central tendency than the mean. I can agree for that simply because of the fact that there are, I mean, look, just qualitatively just looking to the data, there are zeros, twos, and threes, many, and only few extremes of 9s and 16s. So this tendency, so this tendency indicator of 2 is going to be a 2 and 3 is going to be better in such instances. Whereas if you do the math and calculate the absolute absolute mean, it may be something like 5.6 or 6 point something, but which is not the case. On a typical day, 2 or 3 internet failures are the most frequently occurring number. So I could agree to that also simply because of this 16 and 9 becoming extreme values. My suggested answer is answer D. A, B, C, and D are correct. Okay, theory question I'm going to skip. My answer is answer A, where A and C are correct. We have discussed all these points. Last couple of questions for the day. Following set of data gives mean weights of 4 items, A, B, C, and D, which vary independently and their corresponding standard deviations. Which item has the narrower spread? I told you, see, narrower spread. This coefficient of variation, this indicator can be put it into different ways. Narrower spread means lowest variation or the minimum coefficient of variation. Minimum coefficient of variation. Narrower spread. Items are pretty much tied together, not scattered, centralized. That's the idea. Simple. You calculate the standard deviation divided by mean and get the minimum number. I'm getting the minimum point as 0.05 for item number A. Okay. Coefficient of variation is used to measure the relative dispersion, not the strength. This is a repeating question of what we just discussed. A is the answer, and all others are false. All others are discussing about a two variable instance. This is also a pretty much similar question in 16 March. I would rather discuss these points. Arithmetic mean is representative of the whole data set. I can agree. Value of the arithmetic mean may always represent an actual value. No, not necessarily the case. Maybe a decimal number that can calculate after the deviation. C, arithmetic mean might be distorted by extreme values. Yes, that statement we have discussed. Median is the value of the middle number of the data set. No, that we have discussed. Median always reflects the full range of values. Not necessarily the case. See, not the full range of values. Why the median is only discussing the middle point or the central point. It doesn't care about what is the range. So it's asking about the false statements. I would say B, D, and E are false statements. Okay, so with that, we could wind up the class, but for the completion sake, 2021 January, these two questions are I just pasted from the recent paper, and I really wanted to try these two. I have a choice. I want you to try and then maybe discuss at the next class. Shall we do it like that? Since both these questions are pretty much interested, numerically interested. Take a pause, take a snapshot of these two questions, and try it on your own. Students' mark of statistics for 6 terms were 88, 68, so and so. Considering this data as a sample, examine is clear here. Range and approximate variance for the data set. You have to calculate this. This question is pretty much similar to that 30 example. GPA, average GPA is given. You have to calculate the average GPA and the variance. Try these two questions. We will start from here at the next week. And let me try to see whether, if at all, you have any questions. Always when they ask for the highest variation, we need to calculate the coefficient of variation and see which percentage is higher. Correct. Of course. Don't forget the fact, Imandi, in such instances where you are only comparing two or more data sets. That's where we go and do the coefficient of variation calculation. Otherwise, if you have only one data set, by calculating the coefficient of variation, that doesn't necessarily make much sense, because you can do the same thing by stopping at the calculation of variance or standard deviation. That's the whole idea. You have the average, then you have the standard deviation or the variance. But when you have more than one data set, or that meters and kilograms and cubic meters, those data sets, you need to understand, okay, what is the most varying element. That question of that meters and cubic meters and kilograms, see, it has a cubic area of some cubic meters, it has a weight, it has heights. So the heights seems to be pretty much in line, but the weight seems to be varying from one to the another. That's why when you're comparing more than one data set, more than one basket, maybe 8-watt bulbs, 13-watt bulbs, 15-watt bulbs, so that's where you need to go for the coefficient of variation. And in such instances only, you can compare for the what's the maximum, what's the minimum, which has the highest variation, which has the lowest variation, narrower spread, higher spread. So always look into the angle of the question, whether you're asking for the maximum variation or the minimum variation. That's the broad idea of the coefficient of variation. Yeah, great. So we had a good day filled with numbers. I told you from lesson number 3 onwards, there will be plenty of calculations. So this is just the beginning. Don't forget that there are interesting calculations that are coming on the next lesson. You will curse me for some of the equations that I will ask you to keep in mind. But don't forget the fact that always we are looking at two things. One is the knowledge. Second one is the examination